Carbon dioxide, a basic building block of plant life and an important greenhouse gas. Typically associated with the atmosphere, CO2 has come to play an important role in producing oil from deep in the earth. Today, scientists are looking for ways to address the threat of climate change, and the process of CO2-enhanced oil recovery is pointing the way.
Funding provided by the U.S. Department of Energy, the National Energy Technology Laboratory, the members of the Energy and Environmental Research Center's Plains CO2 Reduction Partnership demonstrating safe, practical CO2 management, and the members of Prairie Public.
Deep in the earth lie many natural resources. Among these are large underground deposits of nearly pure carbon dioxide. For nearly 40 years, this geologic CO2 has been injected into aging oil fields to boost oil production. Scientists are now beginning to apply this oil patch technology to help address the threat of climate change. Our story begins in the American Southwest nearly a century ago in the search for oil. Boyeros, New Mexico, 1916. The Great War had increased the demand for oil. Wildcatters were drilling well after well, hoping to strike it rich. But what looked like success didn't always pan out.
I heard where a guy had a flowing well, and he said, and he was jumping up and down, he was excited as heck, and somebody asked him, don't you think we ought to try to light it? And somebody did, and the match went out. And he went out drilling for natural gas and found CO2. He had the world's finest fire extinguisher.
What the wildcatters had discovered was that pure carbon dioxide can occur in natural underground deposits, just like oil or natural gas.
There are quite a few formations around the country where large amounts of CO2 have been contained for millions of years in natural deposits, just as oil and gas have been retained in formations for millions of years.
The wildcatters soon left Boyeros, but enterprising locals made CO2 an industry. They drilled more wells and used the CO2 they produced to put the fizz in sodas and to make dry ice to keep ice cream cold. While geologic CO2 from northeastern New Mexico cooled the Southwest, in nearby Texas, oil production was heating up. The United States was a leading oil producer, and Texas seemed to hold an endless supply of black gold.
The earliest wells were drilled in the late 20s. Most of the drilling occurred in the 40s and 50s, with a big push for the war effort. Permian Basin provided a lot of oil for the World War II era.
Permian Basin, Texas, the 1950s. Oil production was declining. The black gold in West Texas seemed to be drying up. To understand why, we need to know some petroleum geology.
All fluids in the subsurface are contained in the pore space in between the individual particles that make up the rock. On the screen is a magnified image of the reservoir rock. The blue is the porosity that we can see with our naked eye. We can also look at some of the connections in between the pores, the permeability, the pathway in which fluid or gas will move from point A to point B. Oil is less dense than water, and it will move through the surrounding rock, which is filled with prehistoric ocean water. Because of this buoyancy effect, the oil migrates through nice reservoir rock with the porosity and permeability. It moves up until it reaches a rock that it can no longer go through. If pores aren't connected, fluid and gas cannot move between the pores, and that rock has low permeability.
Those tightly closed rocks are called seals or cap rocks.
Shale layers, salt layers, and a type of gypsum called anhydrite are good seals at depth. If other conditions are right, the seal forms a container and oil will become trapped there for millions of years.
The weight of overlying rock and fluids creates pressure in the oil reservoir. That pressure is key to forcing the oil to the surface. In the oil patch, that's known as primary recovery.
The beginning of primary recovery is just letting the reservoir do what it can. It's down there, it's under pressure when we start. Eventually, the pressure drops low enough that we have to start pumping it.
Primary recovery can produce about 10 to 20% of the oil in the reservoir. In the 1950s, oil companies learned how to use water to get even more oil out of the ground.
Secondary recovery was invented about 60 years ago, and that usually employs injecting water into the oil and gas reservoir, which will raise the pressure back up and force more oil out of the reservoir.
Secondary recovery can produce another 10 to 20% of the original oil in place.
Starting in about the mid-1950s, most of our major fields were put under water flood. By the late 1960s, probably just about every one of our major fields was already in water flood.
With water injection in place, West Texas oil was flowing again. But water injection did not work everywhere.
In the early 70s, the Railroad Commission was looking at one of our big fields on the east side of the basin and said, you know, that we're worried about the future of this field. So they devised a scheme to run it into a specialized recovery technique that would then get a great deal of the oil out. The technique was novel at the time, but it was CO2.
Oil field operators found just enough CO2 byproduct from a nearby natural gas processing plant to give CO2 a try.
CO2 was selected because there was some laboratory tests that showed it to be a method by which you could change the properties of the oil in the formation. Thin it up, basically, and loosen it from the rock, if you will, and swell it. That's really the definition of an enhanced oil recovery process, that one that changes the properties of the oil, allows you to recover more of it.
The CO2 worked. Now the Texas oil men needed a long-term, stable supply of CO2 to take oil production to the next level.
The oil companies needed a very large and very reliable source of CO2 for their oil fields. And so in the late 70s and early 80s, they went about systematically developing some geologic sources that had nearly pure CO2 in them.
The closest CO2 sources that are large sources are in northern New Mexico or southern Colorado. So there are large pipelines which bring over 1 billion cubic feet of gas a day to the Permian Basin for our CO2 floods.
Once it's to the big oil fields where that they wanted to CO2 flood, they then developed a distribution system to inject the CO2. So we've had a history of 20, 25 years now with plenty of CO2.
During CO2 EOR, some of the CO2 comes back with the oil.
When you CO2 flood, we leave in that reservoir about 60% of the CO2. We only get back about 40%. Then we strip that out of the oil and gas and put it back in the ground. But that means that we're constantly buying new CO2 in our CO2 floods.
CO2 enhanced oil recovery was like discovering new oil without drilling new wells.
1 billion barrels of oil has now been produced as a result of CO2 flooding. And we anticipate in the future that we may see another 10 billion barrels of oil in the Permian Basin produced by the additional tertiary recovery using CO2 flood.
Geologic CO2 was critical to keep the oil pumping in Texas. But CO2 also plays a critical role in the atmosphere as a greenhouse gas. It helps keep the Earth warm and habitable.
Without CO2 and other greenhouse gases, the climate of the Earth would be much like North Dakota on a cold January day, sunny and 0 degrees Fahrenheit. Way back in geologic time, 500 million years ago, the Earth's climate was much hotter, and the amount of CO2 in the atmosphere was more than 10 times what we have today.
One question that might be asked then is, where did all the carbon dioxide go? Well, Mother Nature actually sequestered some of that carbon, incorporating it into certain rock types, as well as sequestering carbon dioxide in the form of hydrocarbons or oil, as well as coal.
Every barrel of oil produced to meet the demand for energy also brings ancient carbon back to the surface.
All fossil fuels contain carbon and hydrogen. And to get to the energy contained in these fossil fuels, you have to burn them. And when you burn these fossil fuels, the end products are primarily carbon dioxide and water. The more you burn fossil fuels, the more carbon dioxide you produce, and the higher the concentration in the atmosphere.
Human activities like farming and using fossil fuels have been putting more and more CO2 in the atmosphere for the last 150 years. At the same time, CO2 levels in the atmosphere have been increasing, and the average temperature of the Earth has increased about 1 degree Fahrenheit.
While scientists were puzzling over the mechanics of climate change, the world's appetite for energy continued to grow. In oil basins around the world, oil producers were trying to meet that demand. Williston Basin, Western Canada, 1984. Oil production in the Canadian province of Saskatchewan was dwindling. There was plenty of oil in the ground, but most of the easy oil had been produced.
We're getting close to that economic limit where we'd have to kind of shut in and walk away. And lo and behold, in 1984, they started the pilot with the tertiary recovery or enhanced oil recovery.
We put together a small pilot to determine whether or not CO2 flooding would work in the Midale Reservoir.
CO2 injection or enhanced recovery or using CO2 wasn't anything new. They'd been doing that in West Texas since the 1970s. The biggest difference between what they were doing in Texas and what's going on here is their CO2 was a natural source. Drilled a well, found some CO2, and that CO2 just came up from the ground and went right back down into another formation.
What we did is we trucked CO2 from a plant in Medicine Hat, Alberta, which is about a 5.5-hour drive from here. The cost of that CO2 was quite significant because it's the CO2 that your local bottler of soda would use to make his products.
The CO2 EOR test was successful. The problem was finding a long-term supply of CO2 at a reasonable cost. The solution was just across the border. Beulah, North Dakota, the year 2000. Dakota Gasification's Great Plains Synfuels plant in North Dakota was turning lignite coal into natural gas. And the coal-to-gas process was producing millions of tons of nearly pure CO2.
We started capturing CO2 in the year 2000 and started piping that via pipeline up to Weyburn, Saskatchewan for one of our customers for enhanced oil recovery.
When the Weyburn unit decided to proceed with going to an EOR flood with CO2, they contracted with Dakota Gas to construct a 200-mile pipeline from Beulah to Weyburn. So this CO2 is delivered under pressure by pipeline to Weyburn, and then we have a line coming over here to Midale.
The infrastructure that we had to develop in order to deal with the CO2 after we captured it was first a compressor. The current facility up there has 3 compressors. They're right there at the gas plant, and then right out the back side of the compressor station is a pipe that goes into the ground and runs 205 miles up to Weyburn, Saskatchewan to an oil field. The amount of CO2 that we're sending up there on an annual basis right now is about 3 million tons a year. Since we've turned the valve in basically October of 2000, we have pushed up there something over 13 million tons of CO2.
In terms of CO2 emissions, putting 13 million tons of CO2 deep underground is the same as taking 200,000 cars off the highway. This required a significant investment.
There's $25 million for a compressor, $100 million for the pipeline. The customers up in Canada had to, in one case, invest over $100 million in field preparation and infrastructure. But I do know by their own reports that they have taken that field from 10,000 barrels a day to 30,000 barrels of oil a day. They've been able to extend the life of that existing field by 25 years.
This reservoir underneath us, it's 515 million barrels. And originally, up to today, we didn't even have 30% of it. And even after, with enhanced oil recovery, we think that there might be over half of that oil left.
CO2 provides benefit to the oil companies in terms of allowing us to recover a resource we know is there. We do not have to go and drill for. We can use much of the existing infrastructure in facilities and wells and so on to do this. And yet, when we're finished, the CO2 can stay downhole to the benefit of the public.
The Earth, present day. Industrialized countries are trying to rein in their CO2 greenhouse gas emissions while maintaining economic growth and quality of life. In the industrialized world, nuclear, hydroelectric, and renewables like wind, solar, and biomass produce some electricity. The rest comes from fossil fuels that release CO2. Coal fueled the Industrial Revolution, and oil fueled the Transportation Revolution, and they still fuel our world today.
There's a huge dependence on energy in our country, both for our quality of life and our overall economic prosperity. And a large portion of that energy production is out of fossil fuels, which are carbon-based.
The United States, I think, is a good example of pretty much many developed countries relative to fossil fuel use. That it's about a third, a third, and a third relative to coal, oil, and natural gas.
And the demand is growing as developing countries look for the benefits that energy brings. Coal is the single most important source of electricity in industrialized countries, and the use of coal is growing rapidly in the developing world.
While the United States has led the world in contributing to the CO2 over the last decades, the emerging nations, China and India especially, are rapidly approaching ours, and in fact China has just recently passed the United States in CO2 production, with a great deal of growth ahead of them as they try to reach the same quality of life and energy efficiency and utilization that we have for their overall prosperities.
The obvious challenge is China and India. Their priorities are to bring as many of their people out of poverty as quickly as they can. They both sit on large amounts of coal. They don't want to face restrictions on using that coal. The challenge globally is to allow China and India to develop in a way that doesn't endanger the climate.
The question is really, how will we keep the lights on and have all the other benefits of energy, like clean water, health care, and modern conveniences? We need to look to energy conservation, efficiency, alternative fuels, but realistically, that's not going to be enough. Fossil fuels are going to remain part of the energy mix, especially when it comes to electricity. It's reliable, it's abundant, it's affordable.
We don't think the nation is going to turn off 50% of its energy. If we believe that coal must remain a part of this nation's and this world's energy future, we've got to successfully find the way in which to capture the carbon.
As we look for ways to manage the CO2 from coal, the oil field experience with CO2 takes on new significance. Engineers are using this oil field experience to develop a new strategy for dealing with CO2 from electricity, ethanol, cement plants, and other industrial facilities.
There is a technique called geologic sequestration. Sometimes this is referred to as CCS for carbon capture and storage. Basically, what you need to do in this process is capture CO2 from an industrial source, compress it, put it in a pipeline, transport it to the place that you need to inject it, and then inject it.
And that approach would primarily focus at large emitting sources like power plants, where you could capture millions of tons per year and store those permanently in underground geologic formations.
Most steps of sequestration are well understood from enhanced oil recovery. Others, such as CO2 capture, are still being developed. Right now, it's difficult and expensive to capture CO2 at existing power plants and other industrial facilities.
There are thousands of power plants in the world, and many of them burn coal. In most cases, only about 14% of the exhaust gas is CO2, and the rest is mostly nitrogen with some water and oxygen. It takes a lot of energy to separate that small percentage of CO2 from the rest, and that adds a lot of cost. Engineers and scientists are trying to develop new plants that integrate CO2 separation into the business of generating electricity.
We've taken an approach of trying to find a technology that goes on the back end of the existing plants. That way we can take care of what we got, and then you can always design from there for the newer stuff, and that's how we've tried to approach it.
Although there are significant challenges to capturing CO2 at power plants, oil field operators have nearly 40 years' experience in CO2 transportation and handling.
The pipeline that supplies carbon dioxide has gone under engineering and design, which has safeguarded it for community employee protection and the environmental protection. When we routed the pipeline, it is routed in such a distance from residences and small communities, there wouldn't be any negative impact to the local area. The pipeline has been safeguarded with the appropriate wall thickness, with the proper controls in place with emergency shutdown valves, remote surveillance, pressure surveillance, which would key on any change in operating parameters, which would alert operators at a 24-hour manned facility here at our plant.
Our job is to make sure that we've got all the fail-safes in place, that we limit the amount of CO2 that goes out.
Just as in EOR, CO2 for sequestration is injected at just enough pressure to enter the reservoir, but not enough to damage it.
When carbon dioxide is injected to sequester it, first of all, it's taken up to a pretty high pressure, so it's converted into almost a liquid state, and then it enters the pore spaces in the rock, and it displaces what is there, which in some cases is going to be crude oil, but in most cases is going to be salt water or a brine that's there. It's going to replace that brine and move it away from the injection site. As it's injected, it will rise up against the seal rock, and then it will migrate out away from the injection site.
Geologic storage zones that can hold CO2 permanently are a critical element of geologic sequestration.
To sequester correctly, we need to separate the good from the bad. To identify and separate good sequestration zones from bad sequestration zones. This isn't new science. This isn't new technology. This is basically what oil companies do in their search for hydrocarbons.
It starts with having some storage space for the carbon dioxide to go into. It's going to have pore space. Those pore spaces are going to have to be connected to each other. So when you pump the carbon dioxide in, it can move away from the injection site and out into the storage reservoir. Along with that, you need a seal above the formation that you're going to put the CO2 into, a competent cap rock that is free of fractures and pathways that the CO2 can escape through.
There are three types of geologic zones under consideration for CO2 storage: oil and gas reservoirs, saline formations, and unminable coal seams.
Oil reservoirs have proven over millions of years that they can hold buoyant fluids like oil and gas, and so we know that they have competent seals.
There's still more to learn about saline formations and unminable coal seams before we begin to store CO2 in those types of settings. For example, saline formations occur around the world, but their suitability as a container is completely dependent on the local geology. The key there will be finding the right geology that truly has an effective seal.
Because of the experience gained through CO2-enhanced oil recovery, oil and gas reservoirs are already being tested for the geologic storage of carbon dioxide.
Oil and gas fields are the logical place to begin implementing geologic sequestration. We know these are safe storage containers because they've been holding oil and gas for millions of years. There's already experience operating the CO2 handling system safely in these settings.
The technology used in oil and gas exploration will be the technology of carbon sequestration. The drilling apparatuses, the drill bits, the pipes, the tubing, the pipelines, the separators are all technologies that we understand. We know they are safe because we have been using them for decades in oil and gas exploration and production.
Enhanced oil recovery is a way to fund a lot of the infrastructure that we need to fund to deliver carbon dioxide to potential sequestration sites. It also will help fund some of the infrastructure for the capture and transport, and it'll teach us a lot as well about how to monitor and manage and verify these sequestration projects.
Scientists and engineers are modeling the behavior of CO2 in underground reservoirs. In the Williston Basin, enhanced oil recovery is already teaching us more about monitoring for CO2 sequestration.
Shortly after Encana began its CO2 EOR operation, the Weyburn oil field became the site for an international study on every step of geologic sequestration. When Apache Canada began its own CO2 injection, the Midale oil field joined the research project. Other places around the world are hosting research projects where scientists are studying implementation of geologic sequestration in their area. The research projects are helping to determine the best ways to monitor CO2 injection to ensure safe and efficient sequestration.
We're all looking for the same goal, is what are those best practices? Does CCS work? Is it a viable technology? We're working with the International Energy Agency Greenhouse Gas Weyburn-Midale Storage and Monitoring Project. We're also working with the PCOR group, run by the University of North Dakota, the EERC, in our other project in Zama, to develop best practices for measuring, monitoring, verification, to ensure that we don't get leakage of CO2. The public needs to know that it is safe, that it is a viable technology to safely store for an indefinite period of time carbon dioxide.
We are convinced that there's no significant health and safety issues posed by CCS. The risks are well understood, and the methods for managing those risks are also well understood.
All of these sites will be selected only after an extensive process by scientists and engineers. And we are emerging with best practices that are going to help us to make sure that sites that are selected are safe, permanent storage opportunities.
A wildcatters dry hole in New Mexico 90 years ago led to the production of an additional billion barrels of oil in the Permian Basin. That, in turn, inspired CO2-enhanced oil recovery using anthropogenic CO2 in the heartland of North America. Now, CO2 and EOR are playing another important role, laying the groundwork for a new era of carbon management.
There's no silver bullet to solving climate change. It's going to require a very wide range of technologies, some of which are already developed and commercial, others of which have not been invented yet. We probably have enough capacity on a global basis and in the United States to handle several hundred years worth of emissions from coal-fired power plants and other industrial facilities.
We have some time to develop technologies such as carbon capture and storage to make them more efficient, to make the monitoring and measuring of stored carbon more effective, to bottom out some of the environmental concerns.
Government has a role to play in putting the legislation in place, putting the rules and regulations in place that assure industry that the risks are tolerable, that the monitoring and verification of these projects is not going to be so onerous that they can't afford to do it.
We believe very strongly that coal must remain a part of our energy future. And in order to do that, we have to find the technologies to utilize it more efficiently and effectively. In order to do that, it takes time as well as it takes money. We got ingenuity, we got motivation, we've got the desire to make it work. As a nation, as a world, we're going to get it right. And we're going to continue with the ability to utilize fossil fuels. I won't be here obviously in 2050, but my grandkids will. And so that's what drives us. That's what I think makes us want to do the right thing.
Funding provided by the U.S. Department of Energy, the National Energy Technology Laboratory, the members of the Energy and Environmental Research Center's Plains CO2 Reduction Partnership demonstrating safe, practical CO2 management, and the members of Prairie Public.